Well, hey guys. So welcome to Balancing Chemical Equations. This is going to be a little bit more, it's totally new, and it's going to be a little bit harder than, just your average day of just like learning something, someone telling you something. And it's super important for high school. You do it in Science 10, you do it in chemistry, in your chemistry section in Science 10. And so in my opinion, this is probably the most important thing we do in science all year. So what I need you to do for this video is you need to, one, know that it's going to be a little bit longer. Two, you need to have a piece of paper and a pencil somewhere, or like you need to have something to write with, because if you don't engage with this and you just watch me talk, you won't have a clue what's going on. So if you text me at some point or you're saying like, I don't have a clue what's going on, probably it's because you watched this video without having a pencil and a piece of paper in front of you and you weren't following with me. So that's the most important thing. So pause this video right now and get yourself a pen and a piece of paper and let's get to it, because you need to engage and be with me in order for this to work out, okay? So here we are, how to write chemical formulas. So we need to know this first thing about compounds. And compounds are made up of different elements, usually two, but you could have three, you could have four. So something that you're familiar with is water, which is H2O. So water has two hydrogens in it. And since there's no number beside the O here, it only has one atom of oxygen. Cool. So that makes there be three atoms, two hydrogens, one oxygen, making a total of three atoms in this compound. Other things that are compounds are carbon dioxide, CO2. You've seen that before. So here there's one carbon atom and there is two oxygen atoms, making a total of three atoms altogether. Two oxygens, one carbon. So when we draw molecular diagrams, you learn how to do this in Chemistry 20 and further on into different chemistries. We're not really concerned about the right way to do it. We're just more concerned about the fact that we know that in water, it's made up of two hydrogen, and I call them balls, hydrogen balls, just for fun. Okay, and then one oxygen. And you connect them like this because they don't like each other, they're polar, and they kind of resist, and so that's why they go in this like kind of triangle thing. NaOH actually has three different elements. Na is sodium, you find on your periodic table. O is oxygen, you find on your periodic table. And H is hydrogen. So it has three different pieces to it, and you can build it something like this. So we did some notes in our notes. We can look back later and understand how to count those up. But right now we're concerned about these things called ionic compounds. And ionic compounds is what we're going to do. It's what you've been working with and seen all your life, but now we're going to look at it. So the first thing that I have here is a periodic table, and you have to know that metals are on the left-hand side, okay? And so all of these right here are metals, and that non-metals are on the right-hand side, and so these are all non-metals. Something super important to know is that metals always have something called a positive cation. So they have a plus. If I look into my notes here and I zoom in right on sodium here, you'll notice at the top it says +1. It's a metal, so it's plus. If we go over to iron, which is Fe, you'll notice that it has three forms, +6, +3, and +2. It's always going to have a tiny little number in the top that has a plus. When we look at nonmetals, nonmetals are always negative. And so if we look at something like oxygen here, you're going to notice that in the top corner, it says -2. So it's negative, okay? And that's called an anion, negative. It doesn't matter. You just need to know that metals are positive, that nonmetals are negative. And so all of these have negatives in the corners for them. So that's what's really important to understand. Looking at something like boron, boron is on the stairwell, and boron has a +3 because it doesn't know what it is. It's a metalloid, so it's confused. Don't worry about him, but the rest of these nonmetals are negative. The rest of these metals here are all positives. You have to know that, okay? When you make an ionic compound, you put a metal and a nonmetal together. They're like totally jonesing for each other. They like each other. They're attracted to each other because, you know, positives and negatives attract, just like a magnet. So check this out. When you put sodium, which is Na, happens to be right here, and chlorine together, which is over here, you get something called NaCl, or sodium chloride. It makes, honest, the table salt, tiny little squares of table salt. So whenever you put a metal and a non-metal together, it makes a solid, just like salt. So you always put a plus and a minus together. So how do we name ionic compounds? This is where we have to get into things, and you need your pencil and your paper to figure this stuff out. How to name ionic compounds. KBr. All right, so just so you know, there's always going to be one metal and one non-metal in this ionic compound. So that means that there's going to be one thing from the metal side and one thing from the non-metal side all the time, all right? And so coming up here, we have the K. K means potassium, okay? It means potassium. If you look up the letter K right here, it says potassium, number 19. And so we put the name of potassium first. Potassium, the metal name first. Right beside that, we put the non-metal name, so Br. Br is located on the other side of the periodic table, and it's called bromine, Bromine, bromine. But when we name ionic compounds, we change the IDE, we change the INE, bromine, we change this part to IDE. So you'll notice down here, it tells you that you write the non-metal plus ide. You take away the INE and you always end in ide. Chloride, iodide, phosphide, nitride, everything turns to IDE. You don't say potassium bromine, that would be wrong. You take out the INE and you substitute it for IDE. Super important. That's really the only rule that you need to know. So let's look at this one. Lithium happens to be on this side of the periodic table, and fluorine happens to be way over here. Now we know we can't say lithium fluorine because INE isn't acceptable. So we change that to be lithium gets to stay its full name, the metal doesn't change, and then fluoride, IDE. Easy peasy, lemon squeezy. That's all you've got to know for this sort of stuff. This one, magnesium, Mg, chlorine, well, we can't say magnesium chlorine, we can only say magnesium chloride, non-metal plus ide. That's how you name ionic compounds. You change the INE of the non-metal to be ide. So here's a you try. So what's going to happen right now is I need you to pause the video and to write down all of these ionic compounds and the correct name. You need to use the periodic table. If you have your own periodic table at home, you can actually use that. It's actually a little better than the one I've posted, but that's okay. If you don't have this, you can just use the one that's in my notes and pause it there and have it help you. All right, so I'm going to go ahead and process through the answers. Pause the video now. You do it. Check in with me in a sec. All right, sounds good? Perfect. All right. So I'm going to go ahead and now answer these questions by looking at my periodic table and by figuring out what it's called. So the first one here is actually called sodium oxide. And we need to remember that we changed the oxygen, change it to the IDE. So that's kind of weird, but it's true. This one is nickel sulfide. This one is calcium iodide. Okay, again, we don't say iodine, we say iodide. This one is barium phosphide. So just making sure that you have IDE on the ends of all of these words, and you are for sure able to get these right. Awesome. Next thing, how to write chemical formulas. Well, here's the deal, you guys. Chemical formulas are similar and they make up the name, but now we have all these numbers and letters that we've got to put together. This is the hardest part of the video, and this is where I need you to be engaged with me. So the first thing that I've written here, as you notice, it's barium chloride, BaCl. But the weird thing about it is that there's this little 2 on the bottom of the chlorine. Okay, this compound is made up of 1 barium and 2 chlorines. Well, why? How does chlorine get 2? That doesn't make any sense. Well, if we take a look at what's going on here, we actually need to take a look at both pieces of the periodic table. Barium has +2 in the corner, okay? So you need to know that the charge is 2. Chlorine has a -1 in the corner, so it has -1. So the first thing that we're always going to do when we're naming chemical formulas is we're going to make a chart. It's the rule that I have for all grade 9 students, no matter how good or great you get at this, just to ensure that you don't ever forget it for high school. So my chart just kind of looks like a little bit of a cross here. You can do it on a piece of paper yourself. And so if I had a piece of paper in front of me right now, I would make my little chart just like this. In the top corner, you're going to write barium, Ba, and you're going to write what the charge is, 2+. I found that from the top of the periodic table. Chlorine has 1-, so I'm going to write that there. And then I'm going to put the charges in my chart. If you notice in the chart that I'm looking at right now, barium has 2+ and chlorine has 1-. And I think about this in candy because it's important to think about things in candy. And I think about this like bubblegum packages. So barium, when you buy barium bubblegum, you get 2 pieces of gum in one package. Do you notice that? And when you buy chlorine, you only get 1 piece of bubblegum in the package. So balance means that in the nice little chart we've made, it's 100% equal. There's got to be the same amount of pluses that there are minuses in order for something to be balanced. So right now, this is not balanced. 2 bubblegums to 1 bubblegum ain't balanced. And if I give you the package of 2 bubblegums and I only get the 1, I'm going to be mad because I want my bubblegum. So balance means we have to do something. Balance means equal charges on both sides. So barium comes in packages of 2, chlorine comes in packages of 1. Looking over here in the new table. How do we balance? Well, the first question that I always ask you is who needs more? Does barium need to be balanced and need to get more to be fair, or does chlorine need more? And the answer here is obviously chlorine. It doesn't have 2 bubblegums in a package. It needs more to get balanced. So it's the one that's going to get the number, not barium. Okay, how many packages of chlorine do you need to buy to be fair? So that when I give you a barium bubblegum package of 2 bubblegums, how many chlorine bubblegum packages do I need to buy in order for me to have the same number as you? And the question is, the answer is that you need to, in the end, buy 2 chlorines to balance 1 barium. Lots of people get this part confusing because they say, well, dudes, I only need 1 more bubblegum package. And so I only need 1 more, and that should be my answer. But that's not how you look at it. You need to say, how many altogether do I need? And so that's an important statement that I use. So because here, if you look on my chart, once you buy 1 more package of chlorine, you get to 2 packages. But the thing is that chlorine has only 1 negative. And so basically, altogether, you need to buy 2 chlorines to make 1 barium. Does that make sense? So if I go to the store and I buy 2 chlorine bubblegum packages and I buy you 1 barium bubblegum package, everybody's happy and that's fair. So when we write our equation, and so you'll see here this altogether thing. When we write our equation, we're going to write Ba. He didn't need any more. He doesn't get a number. So barium doesn't get a number. He had the most. And then chlorine, see this? Cl2. It needed to have 2 electrons, 2 bubblegum packages to balance it. So it needed 1 more chlorine to balance. And all together, that's super important. All together, it needed 2 of those packages to balance out barium. So super important. We have to think multiplicatively. That's a weird word, but you have to think about it in multiplication sense, okay? If you start with 1 chlorine, what times 1 is 2 bariums? Well, 1 times 2 is 2. So that's why chlorine gets 2 and not just 1. So that's important. We think multiplicatively, all right? So barium chloride, the formula is BaCl2. That might have been super confusing, so we need to just practice this stuff in order for you to get it. So here's another one. Sodium and chlorine. First thing you look at, +1 in the corner for sodium. You've got to make a chart. Always the rule. So here's the chart coming on in. We put a plus right underneath the sodium. Chlorine has -1 right here. So we put a negative underneath that one. And then we ask ourselves, Is it balanced? Did everybody get the same amount of bubble gum? Hey, guess what? Each package of this comes in one. So because they each have one package, they're balanced. So nobody needs any numbers in this chemical formula. So the answer to this question is just NaCl with no numbers because they had balanced. And so we don't need to give anybody more packages to balance out the unequalness of the charges. Okay, seems simple. Here's the next one. This one, calcium is a +2 and bromine is a -1. When we make our chart like we're supposed to, just like I'm showing you right here, you'll notice that 2+ for calcium, there's 2 pluses for calcium and 1 minus for bromine. This is the same story that we did before. Who needs more? Chlorine needs more, or sorry, bromine needs more. Bromine only has one bubblegum package. How many does bromine need altogether? Well, bromine needs 2 packages to balance out calcium's 2 over here. So the ideal situation here is that when we think multiplicatively, what times 1 is 2? Well, 2 is. 2 times 1 is 2. So the answer to this is calcium doesn't need any other numbers because calcium has the most. So you write calcium first without having to write anything else. All right? It doesn't, because it doesn't need any more, but bromine does. Bromine's at the loss. They need the numbers. So how many altogether does bromine need to balance calcium's 2? Well, they come in packages of 1. 1 times 2 is 2, so bromine needs 2. So this is calcium bromide, and the chemical formula is CaBr2. All right? So that's sort of how we're looking at it. We're looking at it like thinking bubblegum packages. So sometimes things get a little bit wonky, and well, this one actually isn't as hard, but this one is just like this lithium nitrogen. Lithium has +1. Nitrogen has -3. First step, build the chart, -3 on this side. Who needs more this time? Lithium needs more. It's not fair if lithium goes to the store and buys a bubblegum package of 1 and nitrogen's bubblegum packages are 3. They get 3 in their package and I get like 1. So lithium needs more. Lithium gets the number. But the question is, how many lithiums need to balance nitrogen? Well, since there's only one package, you need to buy 3 packages of lithium to balance nitrogen's 3 minus. So 1, 2, and 3. So the answer then to this question here is, and we didn't even write it down, but this one would be lithium 3N. So Li3N, because lithium needed 3 packages of bubblegum right here to balance off nitrogen's 3. Nitrogen doesn't need a number because nitrogen already had 3 bubblegums in their package. So this is lithium nitride. And so this is the formula, Li3N, for that nice substance. All right, so now what I want you guys to do is pause the video right here and with your pen and paper, fool around with these ones and see what you can do. Can you balance these by yourself? If you don't pursue it, you won't be able to do it. So pause it now and I'll show you the answer in just a sec. All right, so this is right here how we do the answers. Beryllium oxygen. Okay, so we write Be with our charge 2+, and oxygen with our charge 2-. We make sure that we write our nice little bubblegum packages inside of the column, and then we ask ourselves who needs more. Well, does anybody need more here? No, because this guy had 1 package of 2, so he's good to go. This guy had 1 package of 2, and he's good to go. So the answer to the formula of this is BeO, and nobody needs any numbers because beryllium oxide is perfect. If we were to name this, we would name this I don't know how to spell it, beryllium oxide, making sure that we finish with the ide. Going on to calcium, calcium has 2+, and fluorine has 1-. You'll notice that I don't write 1 in the minus because I feel like it confuses me. If you want to, you can, but you'll notice how I'm doing it here. So this guy gets 2 pluses, and this guy gets 1-. And so we ask ourselves the question, is it balanced? It's not, because fluorine needs more. So who needs more? Fluorine. Fluorine gets the number. So here's the deal. How many more packages do we need to buy? Well, we need to buy one package to make how many altogether? That's the answer. So calcium doesn't get any numbers. How many bubblegum packages does fluorine need to have altogether to balance? Well, 2, because 2 times -1 over here is 2. And so that's how many we need. We need 2 packages of fluorine to balance calcium. Last one over here is sodium. It has a 1+, and phosphide has a 3-. All right, so who's at a loss? Who needs more? Well, this one for sure is sodium. And so sodium, since sodium needs more, we need to figure out which it balances. So, okay, now let's see here. How many sodium packages do I need to buy to balance off that phosphorus? Well, altogether, I need 3, okay? 3 times +1 is 3, and there's 3 on this side. So I need to give sodium 3 because he's the one that needs more, not phosphorus. So this is your answer right here. And I'll just name these for you in case you want to know. This is calcium fluoride, and this is sodium phosphide. Just notice that I'm putting the "ide" at the end. So here's some more examples that you do need to understand how to do. And this is actually easy. It seems more complex, but it's actually easier than doing the other ones. So I want to just point out for magnesium, it has a +2 and that nitrogen has a -3. So if you look at my diagram right here, you'll notice that I've drawn it. This guy's got 2 pluses on this side and this guy's got 3 minuses on this side. They're not balanced. So I would be so mad if you gave me the bubblegum package of 2 and then you got to keep the bubblegum package of 3. I'd be like, that ain't fair. I want it to be equal. Well, how do we make these suckers equal when 3 and 2 don't go into each other mathematically? They just don't fit. So it doesn't work. So here's the best thing. Whenever 2 numbers don't go into each other, all you got to do is this thing that I call flip it good. Okay, we know that we flip it good in math, but now we're flipping it good in science. Literally, all you need to do is give each other the charge number that's on each other. So you notice that nitrogen had -3 and that magnesium had +2. Well, guess what? All you got to do is give each other your number and you're good. So nitrogen's going to go ahead and give magnesium his 3, if you notice here, and magnesium's going to give its 2. So you actually flip-flop the numbers and you're done. So the answer to this is Mg3, nitrogen 2. Why? Because you flippy dude, okay? You just gave each other their numbers. Why the heck does that work? That's so weird. But this only works when the charges don't go into each other. So why does it work to do the flip it good? Why does it work? Well, I'll tell you why. It works mathematically. So here's the thing. If you look over at my notes right here, you'll notice that magnesium came in packages of 2 and that nitrogen came in packages of 3. Now, I'm a stickler. I want the exact same amount of bubblegums that you get. So the only lowest common denominator or a number that we both can have to make it fair is 6, because 3 times 2 is 6 and 2 times 3 is 6. So get this, in order to make 6, I had to buy 1 package of magnesium, 2 packages of magnesium, 3 packages of magnesium. That made 6. On the other side, when we look to nitrogen, you'll notice that you had to buy 2 packages of 3 to make 6. Now we both have the same amount of bubblegums. But what I really just want to tell you is that all you really got to do when you're balancing out bubblegums and they don't work together is do the flippy do. Because magnesium had 2+ and nitrogen had 3-, and all you really had to do was give this 3 over to magnesium, this 2 over to nitrogen, and it worked. So magnesium 3, nitrogen 2. And it's just because you multiply those 2 numbers together and we each get 6 bubblegums. It's balanced then. Kind of cool. And it's just easy. You don't even have to really understand that part. You just have to know when the 2 numbers don't fit into each other, you just flippy do and you're done. Okay? So here's another example of the flippy do. Okay? I have vanadium and phosphorus. Vanadium's 5 and phosphorus is -3. 5 and 3 don't go into each other. It doesn't work. They don't fit. So all you literally need to do is just give each other the other person's number and you good. So really, you're just going to give the 3 over to vanadium, the 5 over to phosphorus, and you done, okay? So V3P5, that is the chemical formula. vanadium phosphide, and you're done, flipping it good. So kind of cool. And so just so you know, all right? Yeah, so elements that have more than one charge. All right, so super important for you to know. Some metals have more than one charge. This is the other most confusing part of this deal. Some metals have more than one charge, and you have to be able to follow along with me right now on your periodic table. So I've taken a picture of your periodic table because it's better than the one that I have. And I just want to zoom in here and show you some of these things. You know, we were dealing with things that only had like 1+ or 3+. But now when I look at iron, it has 2 different forms, 3+ and 2+. Well, what the heck? Now I have the situation where I have 2 forms of one metal. So how do I know which number I'm using? Iron 2+ or iron 3+? Or look at the one beside it, manganese 2+ or manganese 4+. How do I know which plus I'm using? So not all metals are like this on the periodic table. Sodium's normal, magnesium's normal, everything else is normal. But certain things like this one, or like chromium, or like vanadium, have 2 forms. And because they have 2 forms, you have to watch out for it. So this is where things get a little more complicated. When elements have more than one form, it looks like this, Fe3+ or Fe2+. Look at all of these different forms that I have written out here for you on my notes. Chromium, and then there's a way to label them, and that's by using these things called Roman numerals. So you'll notice that chromium 3+ is actually chromium, and then right beside it, it's got a Roman numeral 3. Chromium 2+ is chromium with a Roman numeral 2. And so this goes for all of these types of metals, iron 3 or iron 2. Now you guys, listen, this is really important because when I send you to the store to buy a Slurpee from me, I ask you for a specific kind. I hate banana Slurpees. I hate them. And if you brought me back a banana Slurpee, I would be so mad because I didn't tell you what kind I wanted, and you just went and got me whatever kind you thought was good. It's the same thing when we're balancing chemical equations. You can't just pick iron 3 and think it's right, or iron 2 and think it's right. You have to choose the correct kind. So when I tell you to go to the store and I say, I want a Dr. Pepper Slurpee, I want you to buy that for me, not banana. And so you have to specify, and those Roman numerals specify what kind of metal is used. So here's all the Roman numerals. If you don't remember how to write them, this is new for you. They're all right here, how to write them. So look to this notes for reference if you need it. Here's an example here. Iron chloride. Dang it, iron's got 3+ and 2+. Oh boy, so 2 different types of iron to choose from. We've got the red iron, kind of like the banana Slurpee, and we've got the iron is purple, which is iron 2, kind of like the Dr. Pepper Slurpee. So the first thing is you need to make a chart. But in this chart, you're going to have 2 forms. You've got 3+ and 2+. Here's iron 2, and here's iron 3+. All right, so you got 2 different kinds. And so since I need 2 chlorines, my bad. So this is what we're doing right here. We're trying to build this formula, and you're trying to tell me which kind of iron did you buy me at the store. And so here's the deal, FeCl2. I need to find out what made this formula right here. So was it iron 3 or iron 2? We don't know. Okay, so FeCl2. Okay, so which one built this particular compound? Well, let's take a look. We could have used this 3, and since I needed only 2 chlorines here to balance out iron, which one did I use? The 2+ or the 3+? Well, in order to balance chlorine, all we needed was to use the 2+ of the iron because we chose this choice. We didn't choose the purple kind of iron. Sorry, we didn't choose the red kind of iron, we chose the purple kind. No, wait. Okay, no. So what we chose was the red iron to balance out the chlorine to make it FeCl2. The purple iron was 3+, but the red iron was 2. And so to make FeCl2, to use 2 chlorines, we had to use iron 2. And so what we do is we call this iron 2 chloride. And so this 2 right here in Roman numerals specified which kind you used. Super important. This means we used iron 2, the red iron. We must specify which iron we used if there's more than one form, just so that you're not running out and buying that banana Slurpee. So here's the formula right now. Which one did I use? So what we're looking at is this right here, CuO. Which copper did I use? Copper comes in two forms. Copper comes in the red form, which is copper 2, if you notice up here, and it comes in one form, copper 1, which is right here. So which one did we use to make it totally balanced, that we didn't need to use any numbers whatsoever? Did we use the 2 or the 1? So we make a chart. That's what we always do. So we made a chart, and you can see here that I put both options on the side. And so Cu2 is here, it's red, and purple is just copper 1. But oxygen, when I go to look at oxygen, I notice that it has 2 minuses, so right here. So really what I'm wondering is, since I don't use any numbers in CuO, which one balanced? Well, obviously the 2 plus balanced the 2, and so I had to use copper 2, not copper 1. So when you name it copper 2 oxide. You specify with this Roman numeral which type of copper you bought. You always put the Roman numeral in the middle, right between that and the nonmetal. It doesn't go in the front, it always goes in the middle. How to write these formulas. So if you were given the name like nickel 2 sulfide, how would I make a chart to figure out how to put that into a chemical formula? So what you do is you realize that this 2, if I look at nickel, and so I'm just going to peel up here all the way to nickel. Sorry, guys. Just going to run all the way back. Oh, no. To nickel. Maybe I won't. Sorry. Okay, so nickel is... all right, so nickel is, it says that it's using 2. But nickel has 2 forms. It has a 3 plus and a 2 plus. But it tells you which one you need to use. When this says nickel 2, it means that we don't need nickel 3. We just are using nickel 2. So you draw the 2 plus in that spot right here. And sulfur is 2 minus, so you just use 2 minus right there. The 2 tells us that we use 2 plus, not the 3 plus. So when we want to write nickel 2 sulfide out, we just write Ni with 2 pluses, because that's what this 2 is telling me. Sulfur has 2 minuses. Oh, and guess what? It's balanced, so it doesn't get any letters, or sorry, any numbers. Okay? So we only use Roman numerals when the metal has more than one form. So for instance, mercury has +2 and +1. That's when we use the Roman numerals. We wouldn't if it was just lithium, because look, lithium only has one form. We don't need to use a Roman numeral when there's just one thing there. We only use a Roman numeral when there's 2 choices or more. All right, same with thallium. There's 2 choices, so we've got to use a Roman numeral. All right, so what's going to happen now is I'm going to actually get you to pause the video again. This has been a long class, but the deal is this. I'm going to make another video with these answers in it, but I want you to try to pursue some of these on your own and see what you can do by yourself. See if you're doing it exactly right, if you're writing it correctly, and when we talk about correctly, we mean that the letter is small and it's in the bottom, like it's not like kind of floating anywhere. We need to make sure that we're using Roman numerals correctly, all this sort of stuff. So I'm just going to demo the first one for you, and I'm going to show you how to solve these, and then you go ahead and do your practice, and I'll give you the answers on a different video. So the first thing you do when you come into a chemical formula, lithium bromide, is you need to name it. And so to name it, we always write the metal first, lithium. So you might have to find that on the periodic table. And then we find Br, which is bromine, but we can't say bromine, we say bromide. So that's your first part of answering these questions. The second part is balancing it and trying to name it. And I didn't leave a ton of room here, but this is what I'm looking for. So when I go to lithium, I notice that it's just +1. So I'm going to put a +1 here. And when I go to bromine, I notice that it's also just -1. So I'm going to put a -1 here. I notice, does it need a Roman numeral? So does this one need a Roman numeral? Yes or no? Well, lithium only had +1. So because of that, it doesn't. So it's a no, and you're just going to put a no there or an X there. And then you're going to write the formula. Since these guys are balanced, I can just write them just like this. And this is my answer, lithium bromide, LiBr. There's no numbers because they're balanced. So I want you guys to try to pursue this by yourself, and you can come into my answer video after and see if you're doing all of this correct. And go through it at all, maybe try to pause it when you have some time. You do need an active periodic table with charges in front of you, so you could use my notes, or you can use your own periodic table if you have it at home. So that's how you name ionic compounds and how you balance chemical formulas. So hopefully you're with me. Make sure you do this stuff, and I'll see you real soon.